Can I start now?
Yeah, go ahead.
The next topic, we move to equilibrium in compute control through active inference. Here I try to start with active inference and how it influences on compute quantum resources to give a better quality of service and experience. Before understand what is active inference, we need some statistical techniques. First we go through what are the basic statistical techniques needed to understand active inference, then we shift into the actual topic. So the first one, Bayesian network structure learning. The Bayesian network structure learning is use the Bayes theory and convert a given data set into a graph. For instance, I take a small data set of different devices, throughput, buffer utilization, a packet loss, and delay, for instance. So it's a sample data sets which to just understand how Bayesian network and what it gives. Okay? So initially it assumes a Bayesian network. Initially the given data set it assumes as a complete graph, and then it applies the Bayes theory, and I'm not going to explain in detail how it works because it takes 1 hour. So the final outcome is a direct acyclic graph along with a conditional probability table for each variable. So the Bayesian structure learning, what it do, it create a structure which look like a direct acyclic graph, and each variable contains some information which we store this information in terms of a conditional probability table. So what this conditional probability table will give, based on our data set which we given as an input, from this data set it creates a conditional probability for occurrence of each event. For instance, buffer is overflow. For instance, how does the probability it affects some performance? It is approximately 75%. So together with buffer utilization and delay, so it gives like a conditional probability between variables, a set of variables. This is the outcome of Bayesian structure learning. So in Bayesian network structure learning, the arrows indicates the dependency or causal relation, which means happening one will occur another. So the causality, what it shows, the two things are interrelated. One happen, there is a chance for happening other. For example, if someone smokes, there is a chance for cancer. If it rains, there is a chance that the whole floor becomes wet. So this causality relation, there is also chance for misinterpretation. How our human brain thinks. For example, you suddenly come out of your house and you see the rain. You see the floor is wet. You might think it's because of rain, and later you realize it's not because of rain. Maybe someone poured the water, maybe the neighbors poured the water, or there is something happening to become the wet. So what happened when what we expect to be happen, but something different happened, obviously our brain will surprise. So what is the surprise here is that, so we think, we assume something happened, but actually there is another thing happened here. So here the surprise will generate. So what is the surprise defines here as your surprise is high. Your surprise is high, which means your prediction rate is low. Right? So when your surprise rate is high, your prediction rate is low. So this surprise is connected with a free energy. What is this free energy indicates? It's the uncertainty between what we expect but what in real term it happened. It's similar to the rain, and you think it's because it's wet because it's rain, but it's because of some other reasons it gets wet. So What is this free energy indicates? The understanding level, the understanding between the actual process which you imagine, our brain imagine, and what really happened in real world. So this we define with free energy. So what free energy says, as much as free energy or surprises we reduce, as much as free energy we reduce, our prediction accuracy will increase, vice versa. So we know, okay, in our side there is a wet because of rain. Assume that this is true. So your prediction, there is no surprise. It's true that there is a rain outside. So what is your next action when rain is happening? You want to go outside. Usually we keep umbrella with us, which means here we have three decisions. Like one happened, and rain happened. You think there is a rain, it's wet because of the rain. This is the causal relation. And you take an action depends on this, which is take the umbrella. This is your action. So this interconnection between the causal relation and your decision we call as Bayesian inference. So we call it as Bayesian inference. So what Bayesian inference says, based on your existing beliefs, based on the causal relation, you take a sequence of decisions. So this is we call as a Bayesian inference. So what we do with this Bayesian inference, we can use to construct a Markov blankets. So what is, don't worry, there are many statistical and neuroscientific techniques involved here to understand active inference, but I try to simplify it as much as possible. So what this Markov blanket indicates, it's a Bayesian belief, like what action, some action happened due to some cause, and you are taking some decision. The interrelation between these events we structure using Markov blankets, and this structure has some properties. As we seen, a Bayesian network is a full direct acyclic graph, and Markov blanket also direct acyclic graph with a certain definition, which means we will not consider all the nodes in a direct acyclic graph or Bayesian network. We treat as a Markov blanket. We consider a subset of Bayesian network learning as a Markov blanket. So when you pick a Markov blanket from a bigger set of Bayesian network, what we consider the target node. For example, in this example, n is the target node. So we consider all the nodes interrelated, like causally related with node n. We consider in a Markov blanket, but we don't go beyond level. For instance, we consider n is the node, target node, and we consider node n's parent. For example, here we represent with p. P are parents to node n. And second set of nodes we include in Markov blanket are children of n. For instance, C. And we also consider siblings of children or co-parent of children. So we use only these three set of nodes in Markov blanket to make it precise and closely related actions and causal set. So what causal inference defined from this Markov blanket is, so it brings the more causal relations between the variables. So how closely related and how closely the model is learning the parameters is mainly depends on a Markov blanket. So we pick Markov blanket instead of complete Bayesian network structure because like applying active inference on such a large network take a high computation, and we use edge nodes, so we try to simplify. So we pick from all variables whichever the most important and more influencing the system, we are considering them as a Markov blanket, and we apply active inference technique later. Then come to active inference. So what is active inference here is, we try to gain the knowledge from the environment through observation. For example, as we discussed earlier about causality, so when outside is wet, what you imagine, it might be the rain. That is your preliminary assumption. We can also say predict the sensor input. So that is your initial assumption. But what happened? You cross-check with the reality. So when you cross-check with the reality, you understand that it's not because of the rain. Someone poured the water. So that's your observation from the world. And based on this observation, you try to update your assumption, your initial sensory input, and you now update it and change your decision or your mind to, yeah, it's not because of rain, if someone poured the water, then your knowledge is updated. So when next time you check, you imagine this water is because of neighbor but not the rain. So it keep on cross-check and update its belief to make it more realistic. This is where our human brain thinks. So keep on, we update our knowledge according to what happening around our environment. So this is the concept we try to incorporate in computer continuum systems. So how we try to bring this into the system, we use service level objectives. We define some service level objectives within computer continuum systems, and we find like different service level objectives from services, device level, low level, and also application level. And based on these three types of service level objectives, we match together and bring more realistic service level objectives, I can say, which are more appropriate to consider. So we consider service level objectives as one of the input to make the system equilibrium. And we can also take like more metric entire computer continuum, but we don't go that deeper in our work. So we initially take a small set of service level objectives. Maybe in future we think how to take deep service level objectives to implement our technique to make a better equilibrium. So in this, we take one example to demonstrate how the active inference can be applied. So we assume there is an area, we kept cameras, IoT camera sensors, we keep on capturing the data through sensors, and to analyze this data we try to push to edge. So here we don't go until cloud level, we just imagine this one up to edge level. So we keep on capturing with the camera and take the input data, send it to the edge device and do some processing, and then upload to the cloud and make the decision, whatever it may be. So in this case, we know that the quality of the video, and we need to send to the edge device, and this edge device take as it is, or it might be reconfigured before sending, or it might be reconfigured. Reconfiguration here in a sense, changing the picture's dimension, compress the image before it processing or sending. So depends on the network bandwidth or something else. So this is the simple example we consider to our work, and we apply a collaborative edge intelligence. We design a collaborative edge intelligence technique composed with 3 stages. One is continuous model accuracy monitoring and fulfill the local SLO requirements. Here actually we adopt a Bayesian network learning to design the structure and learn the representation from input data, and we apply active inference to make it learn quickly and converts quickly and adopt the situation. And we also incorporate federation model, because we know every time new devices will enter into a compute continuum, it's not efficient or delayed to start from the scratch to learning and making the structure. Instead, we try to federate the learning models to a newly entered system. But here we notice the challenge because of the interoperability, and new devices might not be the same configuration. Then how efficiently we can update or put the models into new devices. And the collaboration between the devices to make it a globally optimal solution. So the SLO fulfillment, we check in a local SLO fulfillment, and then we re-verify the overall, like we make it as a cluster and verify within the cluster how efficiently the overall SLO fulfillment is happening. So the Bayesian network, initially what it do, as we discussed in the previous definition slide, it takes a set of metrics from the computing device. It's not a single computer, but a set of computer device, and we define our own SLOs. Here we consider two SLOs, like one is energy constraint. Energy must be, the computation take energy must be below this, and also delay it not go beyond some threshold. And then, so we first construct the Markov Bayesian network based on the entire data which we have from the devices, and we use our SLOs to pick a right Markov blanket from the from this Bayesian network. So here, Bayesian network, we have several Bayesian network structure learning algorithms in the literature. There are plenty, both constraint and score based, and we use field client search. It's very simple Bayesian network structure learning algorithm. We have plenty of better algorithms, meaning we haven't tried. In future, we will try even better algorithms so to construct a better structure from the given data. And then we pick a Markov blanket. So here, the causal filter we took is 4 edges, like this Markov blanket composed with one main node and four other interconnections with its parents, childs, and co-parent. And knowledge extraction. So what this knowledge extraction here indicates, what we learn from the Markov blanket, we verify is there any SLO is violating our condition from the system. Then we try to reconfigure the SLOs. So we repeat this process using active inference, as it follows 3 main stages. One is take the initial beliefs, which is also called predict the sensory input, and compare the events occurring, which means how the changes are happening in the network. Like, for instance, a particular device might be busy in processing one video or image, and how to reconfigure by active inference observation, active inference agent observation within the network, and it reconfiguring the devices, and also maybe impose the sensor or IoT devices to not send high resolution images. For instance, the network bandwidth go down, so you observe how busy the edge networks in the system. So you decide, like through SLO's adjustment, so you just instruct the main device not send a high resolution image, high resolution video. You might reduce or compress the video and send. Sometimes even edge means the end device or IoT device might send the original video to edge device. It might do the compression process within the edge device before analyzing or transmitting to some other device for the decision. So how this active inference agent changes behavior or action? So we assume we consider three major metrics here, 3 major parameters. One is pragmatic value, which impose our SLOs related to quality of experience, and we consider risk assigned. There is another parameter which summarizes quality of services related SLOs. Along with these two, to control the parameters, we also use information gain. So this information gain balances and give a better result and try to convert quickly. So what this makes, like summarizing the so this active inference, it works like its perception and action cycle. It keep on update its beliefs to reduce the surprises in the future. So first it calculates the surprises. I avoid most of the mathematical formulas here, and retain some of the parameters which you feel which is not necessary, and then calculate the behavior of the evaluated configurations in SLOs. Then incorporate these configurations again back to the system space, and identify the highest score and choose this highest score function as our apply for our next iterations. Then knowledge exchange. Here we use knowledge exchange using transfer learning approach. So here we use a cluster head. This cluster head decides means cross-validate the new device configurations if any new device enter into the network, and it will identify the suitable node if already exists within the system. If it is already available, it will transfer the same model to the new device. In case if there is no device available, it find a unified framework out of all the devices and give an initial beliefs to the new device, and the new device start again means executing active inference and start learning and make it better. Then collaborative learning here indicates. So the first two stages, they try to fulfill the SLOs locally, and the collaborative scaling stage. So it pick the condition of all the devices in the network, all edge devices in the network, and it will monitor the configuration changes, and the cluster head is maintain all these environmental metrics, and it decides a unified framework and try to achieve the service level objectives, global level service level objectives here. So as we take the same use case, which we pick the video and transmitting to the edge devices and check the network conditions, and we consider different devices here, and also different SLOs, which includes the network and time delay, and the success rate of data frame delivery, and the distance the frame is traveled. And also to try the model, we pick different computing devices, including edge, IoT, and applications. We set up different metrics. So we implement and test with the different devices, with like heterogeneous devices of different configurations, and we evaluated various metrics. We evaluated metrics for how the active inference is making better performance, and then how the knowledge extraction works and how it influences on making decisions, and also how efficient it is when streaming processes scale. So we evaluated these three criteria. So due to time limit, I go with only a few metrics here. A full metrics can available in this paper, but I go with a few. So how a Markov blanket imposed on complexity inference, and then based on network interoperability and behavior of active inference agent, and how well it is explained, and also how it affects on surprising compression, and how efficient it is on fulfilling SLOs. The first one is we can notice without Markov blankets and increasing or reducing the number of nodes in the Markov blanket, we can notice the time variation it took to compute to learn through active inference. So what we notice here is that when we increasing the number of nodes, it's keep on increasing the taking more number of cycles. So this is the reason which I mentioned. We are not taking the complete Bayesian network here. Instead, we pick the right set of Markov blanket and apply our active inference due to this reason, to reduce the converging rate quickly and also take less computations. And the Bayesian network interoperability. So here, after we converge, we try to backtrack, means apply again with the learned active inference, and we try to iterate and iterate, and how the Bayesian network is started, like the causal relations are changing from stage to stage. So we iterate until 10 rounds, and we can see more dense causal relations between metrics and SLOs here. And we also see how the agent is explainable in terms of pragmatic value and risk factor and information gain. So here also we notice the increasing the active inference cycle. Initially we notice there is no change to pick, like which amount of frames we need to transfer and pixel size to transfer to make it the SLOs fulfill. When we go active inference deeper and deeper, so we can understand that a particular thick rows which decides like how much frame size and pixel rate will increase the overall performance to identify to make it a better performance. So we identify through agent behavior and then pick the best row and column from these parameters to identify the pixel and frame rate transmission between the devices. We also check the surprises. Initially the surprise level is very high before applying active inference, I can say. And when we applying the active inference on a particular device and also the overall collaborative environment, we can notice the difference, how the surprise is changing. Which means initially the surprise is very high, which means the probability is very low, but very quickly, which means after 10 rounds, it quickly converts to optimal solution. From here onwards, the surprise is almost balanced or getting down. And how streaming rate also we check, increasing the fulfillment of SLOs in both the entire global set of compute continuum as well as a particular device. Here it means taken, the gray line is overall, the overall performance of SLO fulfillment, like global fulfillment. We can notice at one point of time we impose congestion in the network. We inject congestion in the network. Then we find a particular device SLO fulfillment rate is getting down, and as early as this congestion is getting read, and also it increase SLO fulfillment very quickly within 20 cycles. So it's like better than many machine learning algorithms, I can say, and reinforcement learning. It converts very quickly and it take better performance immediately. The overall from 2 sessions, which is like bring human intelligence or replicate human ecosystem intelligence in distributed compute control system, give a better performance and more adaptable and intelligent compute control environment, and also we can increase the quality of experience and services. Active inference is necessarily useful for self-adoption, and it will learn quickly and converts quickly to the optimal solution. In future, as I told, we try to compare how performance difference compared with the machine learning techniques and AI technique. So we feel active inference is giving a better and converging quickly with as less as amount of input data instead of regular machine learning algorithms, but we need to cross-check how efficient it is giving compared with the traditional algorithms. And also, as we said, the complexity due to complexity with the big Bayesian networks is giving complex and taking more time. So we need to check to optimize, also bring deep SLOs into the system. So this also we need to verify in future. Thank you very much for your attention. If you want more information, you can follow these references. First 5 references are summary of this presentation, and the rest you can get more information or some extra links on this. Thank you very much for your patience.
Any questions? If not, then we enjoy a quick lunch, and at 1 o'clock we meet outside in front of the reception. There's a question here.
I just have one question.
I'm sorry.
The compute continuum, there's a somewhat similar concept. I don't know if you've heard of it, called the digital continuum.
Yeah.
Sort of like, how do you have any view on how these things hang together?
So you mean,
Is that a completely unrelated notion or possible thing of that? You may not know that, but I maybe have a view.
I don't have much opinion. It might be like a digital continuum might involve many other things, including data related things. But here we talk only about the systems and devices. Yeah, here we don't talk much about data. Instead, we go more deeper into the systems and system level performances.
Thank you. Sorry.
No, it's fine.
I don't see any further questions, so we meet at 1 o'clock. We have 2 buses.